All right, welcome everybody to Linked List Day. Yoo-hoo! So, linked lists are one of the 5 or 6 different data structures that we're going to talk about in this class, and are traditionally one of the hardest for students to understand. So, I'm going to try and take a different approach today and see if we can get you guys kind of understanding how linked lists work conceptually, and then actually start coding them a little bit by the end of class. Okay, so we'll just start from a blank.cc file, and let's include list, and this is the standard library list class. Okay, so the standard library linked list class is an implementation that you can just hashtag include and you can use it. So let me show you the difference between a vector and a list. A linked list. This is technically it is a doubly linked list, if you guys are nerds and care. All right, so if we have a vector, so we can have a vector of energy. We have to include vector. Hang on. Vector, there we go. Vector ints named vec, and we can have a list of integers named lie. I don't know. Sorry, I don't have any good variable names for you guys. So let's say we want to add some data, like we're going to be reading from standard input, and we're going to be saving the numbers into the vector or the list. So we could do something like this. We could do while true, integer x equals read. Please enter a number 0 to quit. And then if we had an error or they typed in 0, then we break. Otherwise, we're going to say vector dot push back the number and list push back the number. Look, the code's identical. Okay, so far. And if we want to print it, we can write a print function, right? We're going to print back vector and list. And we can just make a very simple print function that takes in a const auto by reference data structure. I don't know. I got no good names for you. Sorry. For every const auto by reference x. So for every variable x in that data structure, see out that variable to the screen and do a new line, and there we go. Okay, so that is a working program. We're going to type in -10 and 200 and 400 and -63, and we're done. You'd see here our vector contains -10, 200, 400, -63. Is anybody, and the list does too. It's the exact same so far. Okay. Anyone confused by this code? Like, this is all basically CSI40 stuff. Instead of a vector, you can make a list and you can push back into it. So far, so good. You guys with me? Yep. All right. Let me show you something a list can do that a vector cannot. You do push front. Add to the front of the list instead of adding to the end of the list. Okay. Why is there a separate not x? So this is going to get triggered if the user creates an error. With the read library, it's actually really hard to actually create an error, but if they sort of metaphorically unplug the keyboard, then read can't read anymore from it, and it'll return, and scene will be in an error state. That happens if you hit Control D. So if the user hits Control D and scene's broken, it quits out of the loop. And then this is checking for x being 0. Okay, it'll probably return 0 anyway, so we probably don't need this check at all. Come to think of it, so we can probably just do that. Okay. All right. So if we push front, though, we're going to be adding to the front of the vector, right, or front of the list. How many people here benchmarked this in their milestone 1 assignment? You benchmarked vector insert at the beginning. And so if you had 1 million people in the vector, 1 million integers in the vector, and you inserted at the beginning, You had to take all million people and shuffle them right one square, right? And then you can insert at the beginning. How many people did the benchmark for this? Let's see some numbers here from the online section, because in the in-person section, one of the guys was like had the biggest test, which was like 1 million, which isn't even that many numbers. The test took 16,000 seconds to run. So not fast. When you have an order in operation, order in's actually kind of fast as far as these things go. Like, it's better than n squared, it's better than n cubed, it's better than exponential, but it's slower than constant running time. With a linked list, push front is order 1. Whereas with a vector, it is order n, because you have to move 1 million people out of the way to put it at the beginning. Okay? And if we run this, we have 10, 20, 30, 40. We're going to get 40, 30, 20, 10, right? Because we're inserting at the front, so it goes back to front instead of front to back. Does that make sense? So the vector, push back, push back, push back, push back, 10, 20, 30, 40. With a list, the first thing we put in the list is the 10, and the 20 comes in front of it, the 30 comes in front of it, the 40 comes in front of it. You guys understand? Push front versus push back. Yeah? Makes sense? Cool. So that's something lists can do that vectors can't. And that's actually like the big think for this class. Okay, so the big think for CSI 41 is, when should I use this data structure versus that one? Okay. When you go out into the world and you code real life projects, your problem will kind of define which data structure you use. There's all sorts of different data structures, and they're good at certain things and they're bad at certain things. Okay. And there's no like right answer for every kind of problem. Like, if you need push front, clearly vector is not very good. List is much better than it. So if you're always pushing and popping off the front and the back, then a list is going to be a better option than a vector. But if you don't ever push or pop off the front, then a vector is probably going to be better than a list. And so what you're going to be coming away from this class with, assuming you finish and learn everything, is we're going to go over 5 or 6 different data structures in the semester. You're going to be like, oh, well, my specific application requires us to merge things together all the time. And you know that a merge operation for a linked list is order 1. A merge for pretty much every other data structure is order n. So you're like, we should use lists. And that's what I want you to come up with. You guys understand? I want you to walk away from this class going like, okay, I need to keep track of what numbers I've seen before. And I need to do that quickly, So, I want to check for duplicates. Like, I've got, people are going to be, I'm working for Ticketmaster now, and I want to know if this person has bought a ticket to the Shakira concert already. How do I do this quickly? Right. And that's what makes me proud as a professor. He's like, oh, well, we should be using an unordered map. We can put all the names we've seen before into an unordered map. And then if we want to see if this person buying a ticket has bought a ticket already, we can just check the unordered map. If they're in there, it's order 1. Very fast lookup, very fast search, very fast insert, very fast delete. Cool. Unordered map's the right answer. And then I go, yay, like this. Okay. Is there another library that is similar to public read? No. So it's something that I wanted when I was in college, and nobody ever wrote it. So I ended up just writing it myself 20 years later. I don't know why. I mean, yeah. It's the kind of thing that there's clearly a need for, but I don't know. Yeah, if you're at home, IOStream, hashtag include IOStream, and have fun dealing with what if there's an error, and you try CNing into an integer and the person types in squirrel and then it breaks CN, so you have to like do a cn.ignore and a cn.clear and pull the data out. Like it's actually really annoying working with CN in a robust and error tolerant fashion. That's why I made the read library. It's really for me, but it's also for you. Okay. So what can we do with a vector that we can't do with a list? Well, first of all, Sort works on a being. It works on a being. Sort works on a vector, but it does not work. Std sort does not work on anything because we have not included it. Should I include algorithm? Good, thank you. Std sort works with a vector. It does not work with a list by default. And the reason for that is the sorting algorithm needs random access. It needs to be able to access element 10 and order one time. Order, element 100, order one time. Lists, you can't access random elements in the list. You can iterate across the list. You can go to the next, go to the next, go to the next. Starting at 0, going to the end, you can do that. You cannot just say, give me element 20. So searching or accessing, like the equivalent of the equivalent of .at, right? Vector.at is big O what? How many operations, so to speak, does .at take for vector? If you're like, if you have 1 million elements and you want to get element 50, if you have 1 billion elements, you want to get element 9 million. It is order 1, right? It is just a single operation, so to speak. You can grab any element out of a vector in order one time. A list, though, if it had .at, which it doesn't, it would take order n time. So if you want to get the 100th element out of a list, you have to start at the beginning and go to the right 99 times to get to element 100. So that's a downside. So if you need random access to your data, a list is not your friend. Vector is. And there's a compromise between the two of these that's called a DEC, that is a linked list and a vector kind of smushed together that kind of gives you the best of both worlds in a lot of cases. But yeah, that's why sort doesn't work. Sort doesn't work because sort requires random access. So there's actually a special sort function just for linked lists. It's a member function. I think it might be the only data structure that has a member function version of sort rather than using the global std sort algorithm. Okay, so let's see this. Our number 70, 20, 100, 60. 20, 60, 70, 100, 20, 60, 70, 100. Okay, so we can sort a vector, we can sort a list. The list one I think is slower. Do you guys remember what the complexity is? What is the big O of sort? What is the big O of sort? You guys should have this memorized. This is actually one of those things that computer science majors should actually just know off the top of their head. Complexity in log n. Okay, all right. Not bad. The complexity is the same. Yeah. So for std sort, it is order n log n, and it is also the same for order n log n for the list class. It is slower though. So from what I recall, if you benchmark it, and guess what's coming up for your next benchmarking assignment? You're going to be benchmarking lists. So you'll get to compare the speed of a vector and the speed of a list at sorting. Okay. Cool. All right. Yeah, I mean, that's the standard library list class. It's, push back, push front. At doesn't exist, but if it did, it would suck. Okay. Do you guys understand? Like, you can just, in general, we use this when we push things to the front and back a lot, and also merge. Merging is the one thing that the lists are actually good at. In general, and I'm sorry to break the bad news to you. Yeah, I don't really use lists that much, honestly. Decks are kind of better at all things. So, yeah. Decks, you can push front on a deck, right? A deck is really like a linked list of vectors. So it's kind of a hybrid data structure, but I like decks. If you need push front, decks are your friend. The only thing they're not good at is merging. So when do I use a list? When do I use a list? Question mark, answer, when you merge a lot, I guess. Or if you're inserting in the middle. So inserting in the middle, which would be like vector dot insert, right? Vector dot insert is order n time. Do you guys concur? Luke, do you agree? Inserting in the middle of a vector is order n? Or is it order n divided by 2? It's order n. We don't care about fiddly things like divided twice as fast. We don't care. We don't care about that. We care about the shape. It's a linear relationship. So inserting in the middle of a vector is order n. But if you were to list insert, if you have an iterator there already, is order 1. So you can insert things into the middle of the linked list in order 1 time. If you got to do that a lot, like if you're doing like a text editor or something, you want to be able to insert in the middle of things. There's more specific data structures called ropes that are used for those. But yeah, that's something the linked lists are good at. They're good at inserting in the middle, inserting in the front, and merging. If you're merging multiple lists together, that's really the killer app for a list. Honestly, though, not many of my applications involve merging very often. So yeah, I don't use lists very often. They're like a 1% data structure for me. If you want to know what my top most used data structures are, you got unordered map, vector, array, and that's it. Those are the 3, maybe 7. Okay. Those are the probably use set more often than array, honestly. These are the top 4 for me. Okay, these are the ones that I use on a daily basis. Lists, you got to know them because it's going to teach you about pointers and stuff like that. As we get into writing linked lists, you'll see what I mean. But I'm going to sort of conceptually sketch it out for you guys first before we actually write code. They don't honestly come up that often, except in job interviews. So in job interviews, linked lists are very, very common. Reverse a linked list is like a classic job interview question. If you have a copy of this book, which I highly recommend if you guys want to work in the industry, it's called Cracking the Coding Interview. It's got tons of sample job interview problems. I'll put this up again if you need to see that. It's called Cracking the Coding Interview. 189 Programming Questions and Solutions by Gail McDowell. Classic book in the industry. And it'll prep you for technical interviews and they grab like interview questions from Google, Facebook, places like that. And linked lists come up all the time. They do. So if you want to think of linked lists as being mostly used for job interview questions, you're probably not wrong. But I do use them. I do use them like 1% of the time. Okay, let me show you kind of conceptually what a linked list looks like. Okay. So a linked list is made up of individual nodes. And each one of these nodes is going to have a next pointer that points at the node after it in the linked list. And it's going to have a previous pointer. I'll call this guy prev. And this guy's called next. This guy's next. This guy's prev. And the next pointer points to the next person in the list. And the previous pointer points to the previous person in the list. And each node in the linked list has some data. If we have a linked list of ints and we're going to hold 10, 20, 30 in it, then it'll look something like this. Now, pointers have a special value when they don't point at anything, right? Because this guy, he's the beginning of the list, right? We've probably got like a head pointer here, and the head pointer is pointing at the beginning of the list. And let's add another person here. Holds 40 because why not? I'm creative. And we've got tail here. It's pointing at the end of the list. So if you want to indicate there's nobody in front of us, you set a pointer to. Is that why it goes one by one while using .at? Yeah, because you can't just jump to element 3. So if you're trying to .at, which again doesn't exist on the list class, you start here at the head, and then you go to the right, and you go to the right, and you go to the right, you go to the right, you go to the right, go to the right, until you get to element 5,000 or whatever. That's why .at, if it existed, would be order n. The standard library people don't like adding in inefficient functions. They want you to write them yourself, and they want you to Google, why is there no .at for a list class, so that you see, oh, it sucks. Don't use it. And if you have to use it, you're probably better off using a different data structure. Because if you need to randomly access elements out of your linked list, then you probably shouldn't be using linked list. Like it's probably going to be more efficient to use a deck. Okay. Good question, Kevin. All right. So in computer science, if you have a pointer that's pointing at nothing, we draw it as a 0, and this is called a null pointer. It's sometimes written as null, sometimes written as 0. In C++, though, we prefer writing null pointer like that. This is the Bjarni approved way of saying this pointer is not pointing anything. Okay. But these options work as well. They're just not. They're slightly deficient, because 0. Like if you look at 0, you don't know, is this a pointer or is this a number? This at least tells you that it's supposed to be. This at least tells you it's supposed to be a pointer, but actually null is just 0 under the hood. So null pointer gives you more type safety. Like you can't assign an integer. You can't say int x equals null pointer. It doesn't work. Int x equals 0 does work, which is why we kind of prefer not using these things. You'll probably see me use it at some point because it's a lot less typing to type 0 than null pointer. But that's just me being lazy. It's not me being a good programmer. So this is kind of like what a linked list looks like. Okay. And if we wanted to do a push front, you can see why this would be an order 1 operation, right? If I want to do a push front, then I'm going to call new, allocate a new chunk of memory. These things are called nodes, so I'm going to call new node. And somebody give me a number to put in here. This guy's next is going to be pointing at him. This guy's previous is going to be pointing at him. Number 21 wins, all right? Put 21 in there. His previous is set to null. And every time I draw one of these things on the notepad here, every time I draw something, like his previous is now pointed here, his next is now pointed here, each one of those things is a line of code. Okay? His previous gets set to null. His data gets set to 21. Each one of those things turns into a line of code. And that's one of the reasons why I like visually drawing out a linked list, because you can see the lines of code you have to write. And I'll actually write the code in a little bit. But there's one problem. There's one class invariant. Do you guys remember class invariants? Things that must always be true. There's one more thing that needs to update here. Anyone know what needs to update? What thing is now no longer pointing in the right place? The head is correct. So the head needs to now move up to here. Head is now pointing at the front of the linked list, and all is right in the world. We're A-okay. All right. So this is conceptually what a linked list looks like. So you can see why it's so easy to push to the front. You just create a new node and kind of hook up the pointers, and that's it. I didn't have to move a million people to the right to make room. I just glue it onto the front. And likewise, with the tail, I can just, if I want to push back, I just allocate a new chunk of memory. And this new chunk of memory might be over here, just conceptually, because these things don't have to be next to each other in RAM, and oftentimes they're not. And so I'll have to set tails next to point to this guy. And this guy's previous is going to point to that guy, and we're going to insert 5 for Luke's, and then his next is going to point to null. And then what needs to update? Each one of these things turns into a line of code, but there's one more thing I need to do. What pointer do I need to move? The tail. Very good. So that is just going to come over here, and that's nice. It's nice having a head pointer and a tail pointer, because then you just add in either direction, push front, pop front. You know, either way, you can just work with them. Push back, push front, pop front, like easy. Okay. So let's look at some code. Okay. Do you guys kind of understand conceptually what's happening here, even if you don't know how to write the code for it? Like, do you guys kind of get the idea of what it looks like, you know, at least in, you know, conceptual terms, you know? Bridges has linked list visualizers and things like that, which help. The drawings help. Excellent. Okay. So we'll just keep this minimized. And so we're going to write a list class. So we're going to write today a class that will supplant the standard libraries list class. There's also another standard library list class called forward list. And this is a singly linked list, which this is a doubly linked list. And let me switch back to this real fast. The difference here with a singly linked list is that you've got just a next pointer. There's no previous pointer. So if you're trying to iterate the list this way, it's no bueno, right? Forward lists can only iterate forwards. And they can't be sorted at all, at least not in the standard library. So nobody really uses forward lists. Yeah, that's kind of like, oh, I take it back. So there is one use for a forward list, which is that there's no overhead for it. So I was talking to somebody on CPP reference, or not, on the CPP subreddit, and I'm like, you know, forward list is like the most useless data structure. And he's like, well, I have a use for it. I will sometimes return multiple things from my function, but 99% of the time, I don't return anything. And forward list has no overhead. So if you don't have anything in it, if it's empty, it's basically free. Whereas, you know, if a vector, you know, when you have a vector, you've got like that internal, you know, array that has to be allocated, got a couple pointers, and he's like, a forward list, at least in Visual Studio, doesn't have really any cost at all when you return an empty list. And so I'm like, all right. Respect. Yeah. Learn something. Is there one for a reverse linked list? Is there one for a reverse linked list? Or, yeah. So reversing a singly linked list is a classic job interview question. Let's crack open cracking the coding interview. Let's see here. Additional studying, Dijkstra's, PNP complete. Let's see. Do we have an index in here? There's no index. All right. Let's check the table of contents. Solutions, recursion, C++, trees and graphs, stacks and queues, linked lists. Yep. So there's a whole section on linked lists here, and cracking the coding interview, and you can see here, look, there's a picture of a doubly linked list and stuff like that. So yeah, linked list, job interview questions. Reversing linked list is a classic question that just comes up at, you know, all over the place in computer science. All right. Yeah, so I don't use forward lists. I think it's just kind of pointless. Yeah. If you guys ever felt pointless, just remember forward list exists. Okay. You're welcome. If you guys ever feel useless, just remember Cookies and Cream's Oreo exists. Actually, I don't even know if that's true. Cookies and cream flavored Oreos. I don't know if that's actually, is it real? Is it real? Yep. Okay. Yeah. So if you guys ever feel useless, remember cookies and cream flavored Oreos exists. It's Oreo flavored Oreos. Mm. There's some kind of recursive joke that we can make here about Oreo flavored Oreos, right? We know you like Oreo, so you put more Oreo in your Oreo. Speaking of which, I'm about to show you guys something new in C++. So, you two, you have your daily caloric intake, yeah. Okay, so let's go ahead and delete these. You can see them on the video if you want. And I'm going to make a class called list. And it's going to be a doubly linked list of integers. Okay. And I'm going to have some class invariants, okay? Class invariants are things that must always be true. Number one is the head pointer will always point at the first element in the list, unless the list is empty, in which case it must point at null pointer. Ditto tail pointer for the last element. And then finally we need like probably a size or something like that. Size will always hold the correct size of the list. Okay. So integer size equals 0. And then we're going to need a pointer front and the back. Okay. So, okay, watch this. Sup, dog? I heard you like classes. So I put a class inside of your class so you can classfully class. Look at this. Look at this. Is this fine? It is fine. It's warning we're not using it, but it's fine. Yeah. So, yes, you can put a class inside of a class. Can main access that? Like if this was in the public section, we can make a variable. If this is in the public section, we could say list : node Bob. That's fine. The double colon is called the scope resolution operator. And that's how you can access things inside of other things in C++. For example, you guys have all seen std : sort, std : vector, std : cout, which I hate because I don't like stds, right? I like not having stds. That seems nicer. However, most computer science people would say this is bad programming technique. You should embrace the stds. And I say it's kind of silly. I don't like typing things. I don't like to have to type. And we can get into that whole argument some other time. But the double colon, the scope resolution operator, can also be used to grab things inside of classes. It can also be used to grab things inside of namespaces. For example, if you guys remember, we have like chrono, : high resolution clock, : now. And so so you can have multiple nested levels of like a namespace and a class and all this kind of stuff. So that's how I would be able to make a class of type node. A node refers to like one of these people in here. If it was public, which it's about to not be. So every node is going to have a pointer to the previous node, and we'll initialize it to null pointer. And every node will have a pointer to next. And it'll have an integer data that is the data that one spot is holding. So this guy's data would be 10. This guy's data would be 20, 40. Okay. So that declares a node class. So every element of the list has a previous, a next, and a data. Okay. But we're going to toss all this into the private section. So now look at this. We cannot access the node class anymore because it's in the private section. And so this is a very clever way of kind of shielding your nodes from being manipulated, right? Because the node class is going to be just plain old data, right? I don't need getters or setters or any of that stuff because it's within the private section of my list class. The only person who can mess with the pointers in the node class is me, the author of the list class. So I don't need to go through all... If you guys look at the /public/list.cc, this is what Mincarelli typed up during the previous class. You can see we've got this node class. I think he's updated it. Thing. When he originally wrote it, it had getters, it had setters, and it was like this long, right? And I'm like, we don't need to do that, right? We don't need to do that. We just need this because the risk when everything's public is that somebody in main will just reach up and erase one of the pointers, right? Like somebody who doesn't really know what they're doing because pointers are scary and complicated, right? Somebody will just be like, somebody that's not you, somebody using your list class will just come up and just be like, nah, I'm just gonna erase that. Or maybe the next points to itself now. And so you try iterating down the list and then it falls into an infinite loop, something like that. It's a real worry, when you make everything private, the only person who can mess with any of these pointers is you, right? And it's your job as the author of this list class to make sure it's all correct. Don't put when you have the pen on the tablet, it takes over my mouse. So do you guys understand? We've been talking about proper class design. And by the way, the first competency exam in the semester is coming up on proper class design. We finally finished on Monday the last lecture on how to do proper class design, object-oriented programming. And your competency exam is going to come out today, tomorrow, something like that. And it's going to be all coding. There's not going to be any multiple choice questions. You're just going to have to code up a proper class design class. And I do not want any person to use ChatGPT to do it for them. Okay? Every person who uses ChatGPT on this is going to get a free trip to the dean's office because guess what? If you fail it, if you don't do it right, then you just have to take competency exam version 2. There is no downside to failure. Just try your best, okay? And I will give you feedback on it and help you and be like, you forgot to do this, okay? Whereas if you ChatGPT it and you get it right, that's the worst case scenario. But, if you, maybe worst cases you get caught cheating, but you don't learn anything. Or if I correct the ChatGPT code, you're like, I don't even know what it means because I didn't write it myself. So just do your best. Do you guys all understand? Like, don't use ChatGPT. Just don't. Tired of it. Tired of dealing with it. It's low stakes. If you fail the competency exam, it's not going to affect your grade. You get to take it again 3 times. There are 4 total takes for the competency exam. Okay. Private is like a shield. Yeah, that's a good way of thinking of it. Okay. And so we need to make an interface, right? So the internals is going to have a node class and a size. The interface, we're going to have maybe a list, constructor. We need to have a head and a tail, right? So we need to have a node pointer called head. It's also equal to null pointer and null pointer tail. Actually, let's show you guys something bad, maybe. Let's show you something bad. Okay. So these are also ways that you can set pointers to null pointer. Okay. So that sets head to null, that sets tail to null. Okay. You can only set a pointer to 0, by the way. If you try setting it to 10, it won't compile. Only 0 is allowed. But even still, I don't like setting pointers to 0 unless I'm just purely being lazy. The reason for that is, again, 0 is an integer. And if you're not careful, like if you say auto, if you do auto, right? Auto head, that's going to be an int. That's not going to be a pointer. You got to be careful with these things. All right. Null is just 0 also. So the C++ Bjarne approved way of setting these pointers to be null is to set them equal to null pointer like that. And it's warning that I'm not using them. I know, I'll get to it, chill. All right, so our constructor could just be empty. That's fine. Yeah, okay. I don't think we need anything more than that. We probably need a destructor, right? Probably need a destructor. I'm not going to do it right now. Probably need a copy constructor. Probably need... I do the copy constructor now. Okay. List by reference, right-hand side equals delete. There we go. Rule of 3. No copy constructor. So I just erased the copy constructor that it would make for me. And we can do the same thing for the... that's too much. And we'll erase the assignment operator as well. Rule 3. So, no assignment operator. Okay. But we still need to do the destructor, but that's a lesson for another day. Okay, so what kinds of functions do we know about on the standard library list class? I mean, we've used the standard library list class down here, right? We were. What kind of functions? Yeah, we can call like list.getSize. You know, get list.size. I would call it getSize, but. Yeah. All right, so .size exists, which I would call getSize, right? Push front, push back, pop front, pop back. Okay, cool. All right. So in our public interface, we can have an integer getSize, which is going to be const because it should not change it. It will return size, and that will make that warning go away. Cool. We're now using size. Right. What about set size? Do we need set size? What would it mean to have set size? Think about it for a second, right? Here we have a list that has 5 elements in it, and I call set size 50, and I set size equals to 50. Yeah, that doesn't make any sense to me, right? Like, no, it's wrong now. Remember, the invariant says size should always hold the correct size of the list. So I am not going to have a set size. I'm only going to have a getter in this case. And this is something you guys will develop a feel for over the years, is that you don't always have to have a getter and a setter for every element, for every member variable, right? Like here, getting size makes sense, but setting the size doesn't make any sense whatsoever. We'll let push back and pop back, push front and pop front set the size. You know, every time we add something, size will go up. Every time we pop something, size will go down. It doesn't make any sense to be like size equals 50. No. Likewise, I don't want to have a get or set for head or tail, because I don't want anybody in main having any access to any of these pointers, right? I don't. No. They should have no ability to touch any of these pointers. It is a safety shield, as Sartorelli says. Okay. So yeah, that's our only getter. It's just going to be get size. Okay, it's not too bad. And so what other functions like pushback? Okay, let's do pushback. Okay. So void pushback. It's a classic void pushback. Taking an integer, new value, new data. So it's going to be a little bit bigger. So here's a rule. Anytime you guys are working with pointers, the first thing you should always do with a pointer is check to see if it's null. Okay? Because if you don't, let me show you what happens. See out star head. Actually, let's just see out head points to data. Let's just do this. Okay. Let's print out the value found in the first node. Thank you. Should be a struct. All right. Everything should be pods. Everything's public in Node. Okay, there we go. So what is going to happen? Because when we start off, our list is empty, right? It's full of void and nothing else. The head pointer is pointing to null. The tail pointer is pointing to null. And we try accessing here what data is held in the head. What do you think is going to happen when I... What do you think is going to happen when I, instead of making a list of events like this... We don't have iterators, so we can't print it like that. Okay, we'll write a print function in a bit. Okay, so what happens when we try printing out the first element of the list and head is null? Head's not pointing at anything. What do you think is going to happen? Head's pointing at 0, memory address 0 in RAM. And we're like, go to memory address 0 and print the value that's in memory there. What do you think the operating system is going to think of that? Any guesses? Are you guys familiar with the concept of a segmentation of violation, also known as a seg fault? So your program has certain boundaries. And if you ever go outside of those boundaries, the operating system goes, seg fault, segmentation violation, and it kills your program. Okay. So you're absolutely right, Marsh. It will crash. And or at least it should. So let's just run it without any aliases, no safety features turned on. Yeah, fine. Dash stat equals C++ 20. Okay. Please enter number, whatever. Seg fault core dump. Okay. Death. Death is what happens. The operating system has memory address 0. And about, I don't know, a meg or so around it. I don't really know how big the area is around it. It has memory address 0 and friends marked non-readable, non-writable, non-executable. So if you ever try writing to that memory address, if you ever try reading from that memory address, if you ever try executing anything of that memory address, then the operating system goes segmentation violation and it kills your program. Okay? So don't do that. This is called a null pointer dereference, okay? The reason why you don't want to do this is because Bret the Hitman Hart will come out and give you problems. So most of you guys probably know Bret the Hitman Hart, the greatest it is that was and ever shall be. But a lot of people don't know that he was a outstanding computer scientist. You can see him... he's got his pads on, you know, when he's ready to code here. And so he's helping these guys debug their program, and they are dereferencing a null pointer and seg faulting. So he's going through the code review process with them right now.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
Yeah, WWF back then, now WWE. So part of the Hart family of wrestlers, right? This guy. Right. His middle name is Sergeant. That's cool. All right. Bret the Hitman Hart. Yeah. Okay. Nicer than the Stack Overflow people is correct. Yes. That's one of the main benefits of ChatGPT, right? Is that it's ChatGPT is far less judgmental than the people on Stack Overflow. Bing AI, it's kind of got an attitude. I don't know. And if you tell it it's wrong, it's like, I'm going to stop this conversation now. You know, like, but you are wrong. Why are you booing me? I'm right. Okay. So the rule when you work with pointers is you always check for a null pointer first. Okay. I'm going to write this down. Rule for working with pointers, and you guys are going to be working with pointers a lot this semester. The rule is always, why are you booing me? I'm right. There you go. Always check for null before using it. Okay. So if our list is empty, right? So this is, you know, case number one, right? We have an empty list. And there's a couple different ways we can check for an empty list, right? We could check to see if size is 0, right? So if the size is 0, or if head is null, or if tail is null, all three of these are equivalent, if our code's correct, which hopefully it is. So we only need to really pick one of these, but I'm just typing all three out there for completeness. So you can kind of see three different ways we can tell if the list is empty. So if the list is empty, then we need to start a brand new list. So let's go over here to OneNote and give me a number that we're going to insert into the list. Those people mean as hell. Yeah. 7. All right. So we are going to create a brand new chunk of memory. And when we call new, what new does is it allocates, it finds in RAM someplace that has room available for this. And it makes room for a previous, for a next, and for a data. The previous is 8 bytes. The data is 4 bytes. And the next is 8 bytes. So it's probably going to allocate a total of 24 bytes of memory when we do that. And if you're like, well, wait, that doesn't add up to 24, you're correct. But even still, it's probably going to be 24. I can double check on that though. And so when you call new, it's going to return a pointer. It returns a pointer to this chunk of memory here. Okay. And so we need to set head to point to this. And we need to set tail to point to this. And then what is the other thing we need to change for our invariant? What is the other thing that we need to keep track of? Size is correct. Okay. And so when you sketch it out, now the question is, how do we do this in code? Okay. So head is equal to tail is equal to new node. We don't have a constructor for it, do we? Let's make the data first. It'll generate a constructor for you, but the order of the parameters in the constructor is the order of things that appear in the list. So I just want the data here. So new data, like that. And then, as Luke said, size plus plus, as did Jacob, size plus plus, and we're done. That's it. We have now made a brand new list. So the head is pointing at the only person in the list. So the first element in the list is the only person in the list. The last person in the list is the only person in the list. And size is going to be equal to 1. So, yeah, that's it. Now, if there is something in there already, if there was already somebody in there, let's actually do this. Case number 2, list has people in it already. Then there's already somebody there. We're doing a pushback. Actually, yeah, you wanted to see if it is actually 24 bytes. Let's find out. So later on, we can have this actually print the whole list out. For now, we're just going to see out size of and node. and quit. 24 bytes. Okay. Yeah. So this tells you how much RAM a particular thing takes up. So 24 was what it printed. So each one of these nodes requires 24 bytes of RAM. Node requires 24 bytes of RAM to hold 4 bytes of data. Right? This is another reason why linked lists are not great. So we're using 24 bytes of RAM to hold a net, essentially. So it's like 6 times inefficient. It's not super good. A vector has very little overhead once the vector is like of any size. And you might be wondering, like, how is this 24, right? Because data, an integer, right, is 4 bytes. And previous is 8 bytes, because we're on a 64-bit system. 64 bits, 8 bytes. All right. So 8 plus 8 plus 4 is 24, right? But it printed 24, Luke. I'm not lying to you. The reason for this, it's something you learned about in CSI 45. It's called alignment, data alignment. These guys, because they're 8 bytes long, they have to appear on an 8-byte boundary. So, which means the memory address they're on has to be divisible by 8. This guy has to be on an address divisible by 4. And so what's going to happen is that this guy's going to be on a memory address divisible by 4. Then there's going to be 4 bytes of unused memory. And then it's going to be then it's going to be next. So we've essentially have 4 bytes of data in our node class here that we're not using. So if we wanted to, we could have a second number. I don't know. Data 2. I don't know. I got no ideas here. And if I run this again, did I delete it? I did, didn't I? Okay. Look, I just added another integer to the node class, and it did not change in size. It's still 24 bytes. So. Yeah, if you have any ideas of what you want this integer to be, knock yourself out. It's just free real estate. Okay. Chicanery. Yeah. By default, it'll just pad the thing because it has to, like, imagine this guy's at like memory address like 8, right? This guy cannot appear at memory address 12, which is where it should be, right? Because that's 4 bytes. So if this guy's at memory address 8, this guy wants to be at memory address 12, but it can't be because 12 is not divisible by 8. So it has to move to 16. So those 4 bytes are normally not used. So if you want, you can just toss another integer in there. It's just free. I don't know. Yep. I don't know what I would do with this, but all right. So if we have people in it already, then and we're going to be pushing to the end of the list. Let's draw out. It's very helpful whenever you work with pointers to draw pictures, conceptual pictures of what's happening here. So we're going to new a brand new person, and that's going to, I don't know, we'll call him new guy. And so new guy is going to be pointing at this new block of memory, which also has a previous, right, and next, and a data, which will be set to 117. This data is going to be 7. Okay. So this guy's previous is set to null. That doesn't need to change. This guy's next was set to null, but that does need to change, right? Because we need to have this guy's next pointing at the new guy, right? We need to change it to be like this. Make sense? What does that look like in code? Node pointer new guy is equal to new node holding new data. Tail points to next equals new guy. That line of code right there says tail's next pointer is now pointing at the new guy. is this right here. That. Okay. What else do I need to drop on here? A couple things. Next, I think the default constructor for these guys sets everything to null. Both the pointers to null. And data to null, technically. Data to 0. So we don't need to worry about next. We don't need to worry about this guy's previous. But what other pointer needs to be set for this linked list to be looking like our example up here? Previous of new guy must point back to other. Yeah. Which we're calling tail, because tail is the end of the list. Yeah. So we need to say new guy. New guy's previous is equal to tail. So the old end of the list, the guy before us, the end of the list next is us, and so now we've got that and that. So the new guy's previous is tail, tail's next is new guy. Cool. One other thing? No, two other things need to be done. What do you guys see on here? Is head correct still? Is head still pointing out the front of the list? What do you guys think? Is head cool? Do we need to mess with it? We're pushing to the back every time. Should head ever change? Nah, head stays the same. Cool. But yeah, you're right. Tail needs to move, right? Because now this guy is the end of the list, right? So tail needs to go and point at new guy. How do we do that in code? Tail equals new guy. That's it. So tail is now pointing at the new guy. And the last thing is size. Yes, so size plus. And that's it. We now have the working pushback. If you want to clean it up a little bit, you could put the size after the if and the else, because it's a little bit redundant having it in both. Yeah, that's it. That's how complicated linked lists are. The print function, though, we want to actually have it print the entire list. And so what I'm going to show you guys here is memorize this. This is how you traverse a list. Okay. So do you remember in like CSI 40 when we learned for loops and it was like for int I equals 0, I is less than blah, I plus plus, and you just do it over and over again. There's a certain pattern to like how you write a for loop that's the same every time, so you don't have to think about it. List traversal has the same pattern. It's not the same pattern, but it has a pattern that you need to memorize. And it looks like this. For node pointer putter equals head, as long as putter is not null. We could write it like this if you want. But remember, null is 0, and so that's good enough, right? If pointer ever becomes null, it becomes 0, and 0 is false, and so this is all you need to type, really. So for node pointer equals head, pointer is not null, pointer is equal to pointer plus points to next. Okay. Oops, sorry, that should be a close parentheses, and we will see out pointer points to data. And that, my friends, is how we traverse a linked list. So starting at the beginning, going one node at a time to the right, and we break once pointer becomes null. So once we run off the end of the tail pointer becomes null, the list stops. Also, if you call print on an empty list, head is null, right? So pointer equals head, so pointer becomes null, it doesn't run the list at all. So if you call print on an empty list, it doesn't segfault, it just handles it very nicely. Okay. So if we're down here and we call list.print, it will print nothing at all. And down here, we can go here and see, ally.print here, and there we go. So you can see, okay, all right, 50, 20, 10, 40, 50, 20, 10, 40. Yay, it worked. Notice that it didn't print anything for the print up top because there is nothing in the list. So this print function here prints absolutely nothing. I put it in there to show you it doesn't segfault. Okay. So, yeah, that is how you can traverse a list. So if I gave you lab time, like I want you to iterate over the whole list and increase every node's value by 10, we could do something like this. I don't know. Pointer points to data plus equals 10. Now each number in the list is going to be increased by 10. $10, $20, $30, $40. And now we got 20, 30, 40, 50. Right? So you can use this pattern to do anything you want with the list, right? Pointer refers to the current node that we're looking at. So as we go down the linked list, putter, as Arthur Dwyer pronounces it, putter is our temporary pointer. It'll start off pointing at head. Is it null? So let's take this step by step. So we got this for loop here. Pointer starts off equal to head, and we check, is it null? Right at the very beginning, before we do anything. That's how for loop works. For loop works by creating a new variable and initializing it, and then it immediately checks, is it null? So is it? Is pointer null right now? This is our list. We got 5 people in it. Is it null? Guys, no. Yeah, it's not. So, since it's not null, we are going to see out the data pointed to by the pointer. And so it is going to print 21 to the screen in this example. Then the bottom of the for loop runs. The bottom of the for loop says putter equals putter points to next. And so that is going to have the pointer point here instead, right? Because here is points to next, right? So putter equals putter points to next. It's now pointing here. We then check again, is it null? Is it null? What do you guys think? It just printed 21 to the screen. Just outputted 21. It's not null, so we output 10. And then putter equals putter points to next. Is it null? Nope. Cool. So we're going to output 20. Pointer equals pointer points to next. Sorry, I can't pronounce it like Arthur Dwyer does every time. Prints out. What would happen if you did not pointer? That means only run the loop if the pointer was null. So if we set it to not pointer, this is going to be... It won't do anything on... It won't do anything... It won't do anything if there's anything in the list. But if the list was empty, it would segfault. So, yeah, don't stray from the pattern at your peril. Okay. So, yeah, so it'll then print 30, and then pointer equals pointer points to next, and then it comes over here. Is that null? Nope. Prints out 40. Pointer equals pointer points to next. So pointer is now pointing to null, right? Because this guy's next was 0, right? So when you say my pointer equals pointer points to next, it's now set to 0. And then the for loop ends. And it has printed out 21, 10, 20, 30, 40. Everything is right in the universe. If you want to see what a destructor looks like, because this code is going to leak memory, right? You guys remember the rule of 3? Anytime you mess with pointers really in your code, anytime you mess with pointers, you need a destructor, a copy constructor, and an assignment operator. And we were lazy enough to delete the copy constructor and the assignment operator, but we still need a destructor, right? That's on our to-do list. Let me show you what it says if we compile this with -f sanitize equals address main.cc. So if we do this and run it, 10, 20, whatever. Okay. we will get a memory leak. A memory leak means that we allocated RAM, we did a new, we did not do a corresponding delete. And so it's going to tell you which lines of code that you called the new on, and it tells you how many bytes were leaked. We had 4 allocations total, right? Because we had 4 numbers. We had 4 news that were not correspondingly deleted. So the answer here is to create a destructor, and we can actually use very close to the same for loop here. There is just one little problem. Okay. So what we could do, we could try doing this, and it's not going to work, but we can try it. So starting in the beginning, going to the end, delete putter. It's very close to being correct, but it's wrong. Anyone know why it's wrong? So we start off, pointer points to head. Is it null? Nope. Delete it. Okay, now dereference that pointer that we just deleted, use its memory that we just deallocated, and go to the next one. And the worst part is it'll probably work, because when you delete something, it doesn't actually erase anything in RAM. Usually we do lazy deletion, where when you delete something, you just need to clear it, not delete it. No, you have to delete. Every new needs a delete. Every new needs a delete. And the problem is this. Market for deletion. The problem is this. Is that after we've deleted it, then we say dereference it, grab the memory there, and go there. Which you can't do, not legally. If I try running this, address sanitizer is gonna pick this up and yell at me. Okay. 1, 2, 3, 4, whatever. Boom, explosion. Okay. Use after free. Use after free. A friend of mine at Microsoft told me that an experienced group of modern C++ developers had a life-threatening bug because of a use after free problem like this. And I asked him if they used address sanitizer, and I'm still waiting to hear back on if they did, because I don't think that, I don't know. It's pretty hard to sneak something past address sanitizer. Like it really is. Yeah, like he wouldn't tell me the actual application, so I was like, you know, it's something that would have endangered human lives by crashing. Okay, that's all he'd say. Did the hand sanitizer kill him? No, he's not a virus. But he's like, I can't tell you who it is. Only that they're experienced developers, and they had, even using modern C++, they still had a use after free bug in their life dependent code. I'm like, it's all right. You can say the word Boeing. It's all right. You know, I know who you're talking about. You're talking about Boeing, right? And he laughed about that. No, I haven't got a message back because I'm asking him to ask them if they know about address sanitizer. Like, have you heard the word and gospel of our Lord and Savior, ASAN? Because it's really hard actually to sneak things past address sanitizer. Like, it really is. Like, it's a really good tool. And we all owe Google a lot of thanks for inventing it. So, yeah, we can't quite do this. We can't quite do this. What we need to do is we need to make a copy somehow, right? We need to make a copy. So maybe we'll do this instead. We'll say while I don't know, while let's see, node pointer putter equals head, and we'll say while putter. Okay. So we will make a temporary pointer, node temp equals pointer points next, delete pointer equals temp. Okay. How about that? Okay. So we make a copy of it. So we still have a copy of the next pointer, which is what we need, right? We copy the next pointer. We then delete pointer, but we've already got a copy of its next, and then we go to the next. So this is a better way of doing that. All right. And let's see if address sanitizer agrees with me. 1, 2, 3, 4. Voila. No memory leaks. No use after free bug. I don't know who these experienced developers are, but this is what happened. Yeah, that's the next version of the Boeing 737 MAX 9. Okay, so that do you guys understand what's happening with the destructor? So basically, we're gonna have Putter running down the list here, but you can't delete it and then use it. Once you've deleted something, you should never reuse that memory ever again, right? Like any pointers that are pointing to it are invalid now, and there's a possibility that the operating system will reclaim it or wipe it out. There's no guarantee it'll actually work. Okay. So what we're doing is before we unallocate that memory, what we're going to do is we're going to just preserve a copy of this. So we're going to say temp is equal to pointer points to next, and then we deallocate this memory like that. Head is going to be dangling. Pointer is going to be temporarily dangling. Dangling means it's pointing at nothing, but it's fine. Head is going away. Tail's going away. Pointer's going away. We're not ever going to use them again. And then, so that's after the first 2 lines of code. So we made a copy. We deleted pointer, and then the 3rd line is pointer equals temp. So pointer points to temp, and we repeat, and we just go down the line doing this over and over again until temp equals null, then pointer equals null, and then it stops. Yep. So that's a working destructor for a linked list class. So what you guys, I don't want to do all of them for you because it's going to be a good exercise for you guys to work with pointers and things like that. So maybe I'll give you like push back and pop back, and then you have to do push front and pop front. I don't know. So you've got another benchmarking assignment coming up where you're gonna have to benchmark all this stuff. Your next homework assignment though is just gonna be similar to Class Playground, where it has like a self-testing facility where you have to make a linked list class, and then it runs all sorts of tests on itself. So that'll be given out on Monday of next week. In the meantime, you have imaginary homework and fractionation to do. Both those are due on Monday. On Monday, you're going to get the first linked list assignment. That'll be due the following Wednesday because you have Friday and Monday off. And then on that day, which is going to be... so imaginary homework's due on the 12th. You're going to get EU4, which is our linked list assignment, on the 12th. The 16th and the 19th are off. So on the 21st, it'll be due. Then on the 21st, you're going to get your next big benchmarking assignment. We're going to work in groups of 4. Minkrelli and I have all of your peer reviews and stuff like that, and we're gonna put you guys into teams based on the feedback that you've given us on the first benchmarking assignment. And that is it for today, guys. Thank you for coming out. Hope post your thoughts on linked lists in the chat down below, and we will continue this next time. Peace out.